Sir, may I start?
Yes, sir. হ্যাঁ, শুভঙ্কর বাবু স্টার্ট করুন। Do start.
Good evening to all. To my respected Professor Dr. Deobroto Mitra, our esteemed chair patron, Professor Dr. Giridhari Panda, distinguished speaker Dr. Chanchal Chakraborty and Dr. Devmallu Roy, respected faculty members, my dear students, researchers, and all the participants joining from across the globe, a very warm and heartfelt welcome to each one of you. On behalf of the Department of Chemistry and in collaboration with the Department of Physics and Mathematics and our IQAC, it's my privilege to welcome you to this international webinar on current trends in chemical science CTCS 2025. We are living in the age defined by scientific innovation, a time when chemistry is not just a subject in textbooks but a dynamic force driving real world change. From sustainable energy to smart material, from nanoscience to computational design, the frontier of chemical sciences are expanding faster than ever. This webinar is our humble attempt to bring some of these frontiers closer to you, to inspire, to inform, and to ignite conversation that matter. Today's program is thoughtfully organized to explore two groundbreaking themes in modern chemistry. In our first technical session, Dr. Chanchal Chakraborty will talk us into the world of the redox active polymer, exploring their role in sustainable energy system from smart windows to advanced energy storage. In our second session, Dr. Demal Roy will guide us through the realm of computational and material chemistry, focusing on photovoltaics and single molecule magnets, a fascinating intersection of theory, simulation, and application. Both sessions will be followed by the interactive question answer, and I encourage each one of you to participate actively. Your questions are not just welcome, they are essential to spirit of this dialogue. Before we proceed, I would like to express my sincere gratitude to our leaders, Professor Mitro and Professor Panda, for their constant support and guidance. My thanks to all the organizing committee, our technical team, and every colleague who worked behind the scene to make this event possible. To our speaker, thank you for sharing your time and expertise with us. To our participant, thank you for choosing to spend your evening in the pursuit of knowledge. Without further delay, let us begin this journey of discovery. I now have to honor to invite our chief patron and principal professor Dr. Giridhari Panda to deliver the inaugural address and formally commence this webinar. Let me introduce Dr. Panda. He has published more than 80 research papers in various journals, delivered speech more than 60 national and international seminars. Two PhD scholars completed PhD under his supervision, and 5 PhD scholars contributing PhD under his guidance. With this brief introduction, I invite him to inaugurate the session. Sir, please come. Now the online platform is for you. Please, sir.
Thank you. Om Nilatala Nivasaya Nityaya Paramatmane Balabhadra Subhadrabhyam Jagannathaya Namah. Yathadipo Nivatasto Nengateso Pamasmrita Jnanasya Paramang Rupam tadeva vidusang matam. Just as a lamp placed in a windless space burns with unwavering clarity, so does true knowledge shine luminous and enduring when cultivated with discipline and reverence. Respected Chairperson of Governing Body, Professor Dr. Debabrata Mitra, former Vice Chancellor, Dakhin Dinajpur University, and Professor of Commerce, North Bengal University, respected speaker Dr. Chanchal Chakravarti, Assistant Professor, BITS Pilani, Hyderabad, and Dr. Devamalya Ray, Assistant Professor, Monmouth University, USA, Dr. Shubhankar Sarkar, convener and moderator of the webinar, as well as HOD Department of Chemistry, and other faculty members of the Department of Physics, Mathematics, esteemed scholars, respected dignitaries, colleagues, and dear students. It is my privilege to welcome you to this webinar on behalf of our institution, organized in the spirit of inquiry that unites traditions with contemporary relevance. This institution stands on a land where learning has long been regarded as a sacred pursuit. The region of Dandabhukti extending between the Dwarakeswara and Subarnarekha rivers once flourished as a vibrant corridor of intellectual exchange, pilgrimage, and cultural synthesis. Buddhist monasteries and Brahminical centers of learning thrived here side by side, nurturing a scholarly ethos grounded in Samvad and Samanvaya, dialogue and synthesis. Sanskrit poets such as Vasukalpa, whose verses addressed both the Buddha and Shiva, remind us that wisdom at its highest transcends rigid boundaries and moves toward the universality. It is this civilization memory that quietly holds the vision of our institution since its establishment in 1963 by Mathuranath Bhatter College. Bhatter College Dantan, now an autonomous institution, and endeavored to translate inherited values into meaningful academic practice. Our guiding ideals drawn from the Upanishads, Satyam, Jnanam, Anantam, affirm our commitment to truth, the pursuit of knowledge, and the infinite horizons of the human understanding. Autonomy has further instructed us with a greater responsibility to innovate with integrity, to teach with relevance, and to serve society with accountability. Within this framework, today's international webinar on current trends in chemical science is both timely and significant. Chemistry in the modern world is no longer confined to laboratory walls. It has emerged as a vital language through which humanity addresses uh, challenges of sustainability, health, energy, and environmental balance. Advances in green chemistry, material science, nanotechnology, and computational modeling demonstrate as a discipline striving for harmony between scientific progress and ecological responsibility. As Marie Curie wisely observed, nothing in life is to be feared, it is only to be understood. And it is this pursuit of understanding that lies at the heart of chemical inquiry. At the same time, the ethical dimension of contemporary science has become increasingly pronounced. The integration of artificial intelligence, AI, and data driven research has accelerated discovery, but it also calls for discriminant, and moral clarity. In this respect, modern chemistry echoes an ancient Indian insight that knowledge discovered from values remains incomplete, as C.V. Raman aptly remarked. The essence of science is independent thinking and hard work, not equipment. It, it is the spirit of thoughtful inquiry that we seek to cultivate through this digital international webinar. The academic gathering, therefore, is more than a formal event. It is an invitation to think critically, to engage responsibly, and to connect inherited wisdom with innovative practice. May the deliberation that follow illuminate new pathways of understanding and inspire our students to scholars to view science not merely as a profession but as a service to humanity. With these reflections, I formally inaugurate this digital international webinar and wish it every success. Thank you. Thanks a lot. Dr. Shubhankar Sardar.
Yes, sir. Thank you, sir. Thank you for your inspiring speech. Uh, Now, I am welcoming to our respected President, Professor Dr. Deobrata Mitra, Chairperson, Governing Body, who served as Vice Chancellor, Dakhin Dinajpur University, West Bengal, and acted as an Honorary Director, UGC HRDC, North Bengal University. With this brief introduction, I invite Professor Deobrata Mitra to this online platform to deliver presidential speech. Sir, please come. Now the online platform is for you.
Yes, am I audible?
Yes, sir.
Oh, very good evening to everyone, to our esteemed principal and chief patron, Professor Dr. Giridhari Panda, distinguished resource person, Dr. Devmallo Rai, and Dr. Chanchal Chakrabarti, our digital convener, our diligent convener, Dr. Shubhankar Sardar, dedicated faculty members, students, and fellow researchers joining us from across the world. At the outset, I like to congratulate the organizers for organizing this sort of webinar on this relevant topic on current trends in chemical sciences. Really, it is a wonderful topic, and I think that a lot of researchers all over the world will join in this webinar, and definitely with their very good research experiments and research work. In an era defined by the rapid scientific transformation, and an event like CTCS 2025 is not merely an academic exercise. It is a vital confluence of ideas, a bridge connecting the inquisitive minds of our students with the pioneering spirits of global science. Bhatter College, Dantan Autonomous, has always championed the spirit of knowledge, creation, and dissemination beyond the confines of traditional classrooms. Today's webinar, meticulously organized by our chemistry department in collaboration with the Department of Physics, Mathematics, and IQAC, stands as shining testaments to this commitment. It reflects our unwavering dedication to fostering academic excellence and exposing our learners to the frontiers of global research. The focus areas of this webinar, which I have heard, is centered around material science, energy storage, nanoscience, and the modeling of materials for sustainable and advanced applications. Quite literally, the building blocks of our future. From powering our world with efficient lithium batteries and green electro catalysts to harness the light for photovoltaics and exploring the marvels of single molecular magnets, the topics on our agenda are at heart of solving some of the humanity's most pressing and challenges. We are extremely privileged to have with us two brilliant minds as our resource person, Dr. Devmallo Rai, joining us from Manmat University, United States of America, and Dr. Chanchal Chakraborty from Birla Institute of Technology and Science, BITS Pilani, Hyderabad, represent the very zenith of contemporary research in chemical sciences. Their presence here today is of great inspiration for the institution, that is our institution, Dantan College Autonomous. I am confident that their insights and their thoughtful deliberations definitely ignite the curiosity, provoke thought, and perhaps even shape the future research trajectories of many youth scientists attending this session. I am extending my deepest sense of gratitude to our chief patron, Dr. Giridhari Lal Panda, who has recently joined as a principal in this college, for his steadfast leadership and support. My sincere appreciation goes to the convener, Dr. Subhankar Sardar, and his entire team for their meticulous planning and hard work in bringing this prestigious event to fruition. I also commend the spirit of all faculty members and students who have registered with such enthusiasm. To all our participants, I urge you to engage actively, go on asking questions, challenge the concepts, and immerse yourselves in the discussion that will follow after the insightful deliberations of the resource persons. In conclusion, I believe that gathering like this are the cubicles where the next generation of scientific innovation is forget. Let us all listen, learn, and collaborate to advance the noble cause of science for the betterment of our society and our planet. And I wish this webinar a resounding success and all our participants a profoundly enriching experience. Thank you. Jai Hind. Jai Hind. Thank you so much. All the best.
Thank you, sir. Thank you for your motivational speech. Thank you, sir. As we move into the first technical session of our webinar, it's my great pleasure to introduce our distinguished speaker, Dr. Chanchal Chakraborty. Uh, he has completed PhD in Polymer Science Unit of Indian Association for the Cultivation of Science, IACS, Kolkata. He served as postdoctoral fellow at National Institute of Material Science (NIMS), Tsukuba, Japan. He served as DST Inspire faculty at BITS Pilani, Hyderabad, and now he is serving as assistant professor at BITS Pilani, Hyderabad. Three students have already completed their PhD under his guidance. Presently, six students are doing PhD under his supervision. Dr. Chakraborty is an assistant professor in the Department of Chemistry at BITS Pilani, Hyderabad. His research profile is truly outstanding and preferably aligned with the core themes of our webinar on energy and the material science. His extensive work focuses on several critical areas of our sustainable future. First, conjugated polymer and the metal organic hybrid materials, energy storage devices such as advanced batteries, and energy conversion technologies, including fuel cell and electrocatalysis. A particularly fascinating application in the electrochromic smart windows. The numbers speak volumes about the impact and quality of his research. Till date, he has three patents. He has awarded the Vice Chancellor Award for Best Young researcher in 2024 across BITS Pilani campus. He also selected as an associate fellow of Telangana Academy of Science TS in 2024 and also awarded DST Inspire Faculty Award in July 2016 with a research grant of 35 lakhs by the DST Government of India. Dr. Chakraborty's work has got citation over 3,280 citations. He has published more than 120 peer-reviewed journals in top-tier international publications like American Chemical Society, the Royal Society of Chemistry, and Elsevier. With an average journal impact factor of nearly 6.0, his scholarly influence in future recognized by an H index of 30 and I-10 index of 83. Beyond journals, he has also contributed to important books and book chapters, authoring works on topics like the converting food waste to electricity, the fabrication of electrochromic devices, and the development of fully green batteries. Today, we will be sharing his he Today he will be sharing his expertise on a specific and innovative area of his research. His lecture topic is utilization of redox active polymers for sustainable energy, from energy saving smart windows to indicative energy storage. Please join me in giving a very warm virtual welcome to Dr. Chanchal Chakraborty. Now the floor is yours. Please, sir, start.
Yeah. Am I audible?
Yes, sir, you are audible. Please start your session.
Okay. Okay. So first of all, thank you so much for inviting me, especially Professor Panda and Professor Mitra, and as well as Professor Suvankar basically. So Suvankar was my senior in cultivation of science, and that is why I'm just telling Suvankar thank you so much for giving me the opportunity of showcasing my research over here. And I'll just share my screen. You just tell me that screen is visible or not.
Okay.
Yeah. Is it visible?
Yes.
Okay. So topic is already been told by Professor Sardar. So I'll be just going to first just introduce my university. Probably is known to few of you, but probably is unknown to few of you also. BITS Planning is well known for its engineering aspects basically. So a lot of engineers and a lot of academicians in engineering basically that BITS Planning produced. It's a old institute, initially initiated in 1964 in Pilani by G.D. Bidla. And then it is having, as of now, it is having 4 campuses across India. So Pilani, Goa, Hyderabad, of course, and Mumbai, the recent campus. And another campus is there in Dubai. One proposed campus is there in Amravati, probably will come in next year. So this is the picture for our institute. Basically, you can see it's here in Hyderabad. It is situated in the north side of the Hyderabad. Basically, so let me just so northern outskirt of the Hyderabad. It's a kind of 30 kilometer apart from the Secunderabad station, and overall NIRF ranking in 2025 is 16. University ranking is 7. That university engineering ranking is 11 basically by NIRF. NIRF research ranking is 18. So gradually it progressed, and now actually it is being counted as the premier institute in India. QS world ranking is 668, and it is It is renowned as the first in the private engineering college section, basically by India today and MDRA ranking system. And as a chemistry department, I can tell we are at 401 to 450 in QS World University ranking, and Nature Index ranking for the research output in India is 80. So next, actually, I'll just highlight a few research activity of my group, what I'm doing over here. I just tell my research lab as the electronic functional material laboratory. So basically, we develop the electronic materials, and we use them in different kind of aspects like energy storage. So these are the few publications we did from our lab in recent times. And then, of course, that electrochromic smart window, which is the topic actually today I'll be delivering. And next, electrocatalysis for energy conversion. So here that electrocatalysis for fuel cell, electrocatalysis for air battery comes. And then that electrocatalysis. So basically for this kind of dye degradation, electrochemical dye degradation, all these things are coming over here. And we also do a little bit of that for photo detectors with collaboration of with my other colleagues in different departments. And also that we developed a few nanoprobes for diagnostic use, and that is also, of course, with the collaboration with some biology faculty over here in BITS Pilani. And the today's topic is basically the electrochromic material. First of all, electrochromic material is not that much known in Indian scenario, and that is why it is my duty to introduce this material. Electrochromic material are the material which can change its color. That chromic material, you know that chromic material means material having color. So electrochromic means here the stimuli is a voltage. So if you put the voltage, it can change its colors, and the color can be associated with the redox state. So basically that applied voltage, the simple chemistry is applying over here. You are putting some applied voltage, and that applied voltage is changing the redox state, and associated that redox state, if it is associated with the color, it will change its color. And different kind of applications are there. It can be used in auto-dimming car mirror. So basically rear view mirror in car, that wearable electronics like EC goggles, or even that wearable that costumes, e-papers, and Boeing 787 window. So basically the smart window, basically it's like that, and ECD displays for ad boards, hoarding, and of course that Kindle device. And of course it is used as the EC smart windows, especially for the corporate buildings or even that domestic buildings. You can see that corporate buildings are looking as like that purple from outside, basically purple or even deep violet from outside. So these are basically that electrochromic technology people can be used over there. So this electrochromic materials, gradually it is evolved since 1969. 1969, that electrochromism was first introduced to the audience by Satyen Kumar Dev, Bengali researcher, but he did his work from France. So first generation electrochromic material by means of this metal oxides was introduced. And that metal oxides like tungsten oxide, or even that kind of molybdenum oxide, or even that vanadium oxides, they are used in this category. So basically they can form different mixed valent oxides upon reduction, and that mixed valent oxide can provide some IVCT, intravalent charge transfer, and it can give the color change from colorless to something kind of a blue color. Second generation material was introduced by Dr. Philip Boluin by means of organic molecules and polymers. So first introduced material was the methyl halogen. Methyl halogen, one that redox active organic molecule basically, and that can be reduced to give something color changed from colorless to deep blue. Not only that, different kind of polymers were introduced by Professor John Reynolds from Georgia Tech University, that Georgia Institute of Technology, and they actually got a different that spectrum of colors in different kind of that P-dot kind of polymer, basically thiamine containing polymers. Third generation EC material is basically the transition metal complexes, and it was discovered by Shinobu Toshima from Japan in 1982 with Prussian blue. And the Prussian blue is also, that mixed iron complex, basically, that cyanide complex, and it can have different kind of mixed metal conditions upon reductions, and it can produce different colors depending on the oxidation potential you use. And that fourth generation, and the newest generation, basically, is the metal supramolecular polymer. So metal supramolecular polymer, from the name you can understand that it is basically the metal ligand complex. If you take the ditopic ligand and if you charge the metal ions over there, they will assemble together to give one-dimensional metal supramolecular polymer. But depending on the stoichiometry or even topicity of the ligand, different kind of that structure can be generated. 1D, 2D, 3D structure can be generated. And it was introduced by Dr. Higuchi and Dr. Kurt from NIMS in 2007, and I was fortunate enough to work with this person, Professor Higuchi, over there in NIMS during my postdoctoral research. And the advantage of this MSP is basically you can change different kind of metal, and depending on the MLCT of the metal, you can change different kind of colors over there. You can get different kind of color hue out of this metal polymer. And a brief introduction about the device structure, basically. So a lot of device structure I'll show later. So to give a generic thought of these things, we actually can evaluate the property into different kind of device structures. One is the solution state device, basically, where you need something kind of film over there on the top of one transparent electrode, conducting electrode, basically, that ITO we generally use, indium tin oxide coated glass. On the top of the glass, you have to coat the active material, that electrochromic material over there, and as like the simple that cyclic voltammetry, you can use that film as the working electrode. You have to use that counter and the difference electrode to operate the voltage over there. So that is basically the solution state device. We can use different kind of solid state device also, and that is more practical even. So that solid state device, you have to use that electrochromic layer as the active layer, at least one side of the transparent electrode, and you have to use the gel electrolyte over there, as it is the electrochemical device. So gel electrolyte obviously will be there, and on the top of the gel electrolyte, you can put some charge storage layer, and that can be another electrochromic layer also, or even not. And on the top of that, you have to put another electrode, and you have to give the battery over there to give some voltage inside the device, and according to the voltage, it can show the color change. So in general, we do that for the practical use, we do the solid state device, and few parameters I'll be just telling later. So the first parameter is basically the optical contrast. Optical contrast means that transmittance difference between the states, and then the switching time, how fast it is generating the other state. Okay, so switching time faster means it can be used in something kind of dynamic display. And next, actually, the coloration efficiency. Coloration efficiency is basically the optical density change divided by the charge introduced over there, charge required for this optical density change. And high coloration efficiency is always required for something kind of high efficient electrochromic materials. And another is the optical memory. Optical memory means if you, in the open circuit condition, suppose you have generated one electrochromic state by putting some voltage, and after putting the voltage, you just open the circuit, and in open circuit condition, how long it can persist the redox state or even that color. So high optical memory is required for energy efficient or even that low power electrochromic materials. And in a mechanism, I can tell that electron transfer is basically associated as this mechanism is Faradic, means oxidation reduction is associated with that. So electron transfer between the redox centers is playing the vital role over there. So fully conjugated ligand in any kind of metal supramolecular polymer or even any kind of electrochromic material is required for facilitating that electron transfer swiftly. And non-conjugated ligands sometimes deter the electron transfer, but that is having another advantage also. So switching time will be less. But the thing is that optical memory can be high. Optical memory means in open circuit condition how long it can persist. So if you can reduce the self reduction or self oxidation of this material by means of non-conjugation inside, so you can generate some optical memory. So depending on the demand, you can play with this kind of ligand structure, or even that kind of polymer structure. And any kind of regular arrangement can facilitate the electron hopping also. So that electron hopping also can facilitate the switching time as well as the colors and efficiency. And ion diffusion. Ion diffusion, the integral part in any kind of electrochemical devices like battery, supercapacitor. So if the ion diffusion is basically good, that material can show very fast color change. Along with that, colors and efficiency can also be high. So with this concept, it has that electrochemic material has very much advantages, like they have kind of variable transparency, and interim voltage can show different kind of colors. Very less voltage is required, around 3 or little more than 3, to switch the colors. And operating cost is very low. 5-watt light bulb basically as like the 5-watt light bulb, so operating cost is very low, and less switching time is required if you compare the other smart window technology like that polymer dispersed liquid crystal technology. And the most importantly, it can prevent the solar heat, and it can reduce the need of the air conditioning and the cost for the room cooling basically. One data is showing that in 2018, the commercial building energy consumption survey in the US, it is showing that is 5.9 million US commercial building, they consume around 6.8 quadrillion British thermal unit, which costs around 141 billion of USD, and that is a huge amount. In Indian scenario, if you see that what the consumption of electricity we are using, and if we disintegrate that sector wise, we can see that industry, domestic, and the commercial, so they are the leader in these things. So basically, is a huge amount is consumed by them, especially domestic and commercial, 8 plus 26. But when we go for this kind of that in domestic or commercial building or even in industry, what are the cause for this consumption? We see that AC and fans, they are basically 41%. So 41% of the energy consumption is due to the room cooling, especially the country like India, which is in the torrid zone. Basically, we are getting the sunlight. Fortunately for us, because sunlight can provide different kind of alternative energies like photovoltaics. But the thing is that to prevent that sunlight or even that room heating, we need a lot of cooling costs also. So to cut down the cooling cost, you need to know that how the room heating is happening over there and how it is associated with the sunlight. So solar irradiance, if you see the broad spectrum of the solar irradiance, that 45% of the solar irradiance is basically falling into that visible, 5% is around UV, but another 50% is around that IR. And that IR is most culprit. So basically, IR can excite the gases like moisture, carbon dioxide inside the room condition, and then what will happen? They started vibrating, and they can be excited. And whenever they are coming to ground state, they are actually releasing the heat, and that heat basically elevates the room temperature. And we need the AC. But the thing is that sunlight is coming to the room through the window. And if you can use some smart window technology, that can effectively block the NIR light. And that NIR light, if it is not coming to the room, so basically you can effectively cut down the cost for the AC or even fan inside the room condition. So the thing is, what you need to do, visible to NIR or even transparent to black electrochromism to cut the NIR absorption or that NIR light over there. So you need some NIR absorption electrochromic material over there for the smart window. So in that way, actually, that strategies can be done that if you can take something kind of neutral species for the electrochromism, which is having very less band gap between the that valence band and the conduction band, then what will happen after the oxidation or reduction? They will generate the polar on state or even bipolar on state, so that band gap will further reduce and it can absorb the NIR light then. So that is one strategy. Another strategy, if we use some metal containing material, basically the metallo-supramolecular polymer or metal polymer, then what will happen that you can after the oxidation after the reduction, let's say if you use the cobalt 2, after the reduction, that gap between the T2G and EG you can reduce. Also you can tune the MLCT over there, and you can generate the MLCT over there by this effectively that redox thing, and you can get some absorption over there in that NIR zone. So with this kind of strategies, we have developed a few visible to NIR electrochromic material by means of this conjugated polymers. So thiazole group we have used, that is redox active, and that can give something kind of yellow to blackish color in electrochromism by means of that voltage basically. Also we have they developed porous 3D covalent polymeric framework that can show something kind of yellow to brown color change in this electrochromism. And also this is associated with the electrophotochromism, where that electrochromism is associated with the fluorescence change of this film. And also we developed small molecules and all-in-one gel. Basically that electrochromic, you need the film, but if you can do have the film, all the materials cannot make the good film, especially if the conjugated polymer or even that porous 3D that covalent polymeric framework, if they are sparingly soluble in the solvents. So in that case, actually you can prepare something kind of all-in-one gel, and we have used that, and this kind of tarpyridine containing moiety we used, and we produced something kind of transparent to blackish color electrochromism over there in that gel. Also some metal, that one metallo-supramolecular polymer with cobalt we have developed, and that can show some color change from transparent to blackish color basically, and that can absorb in that NIR zone. But the thing is that they are not that much of that color fastness we did not get, and also that colors and efficiency is also not optimum over there, and we are yet to get that truly that visible to NIR absorbing electrochromic material which can block the sunlight at the highest level. So in that purpose, we developed one covalent organic framework basically. So that covalent polymeric framework through that perylene carboxylic anhydride. So along with that melamine, and that melamine perylene can provide this cough, and that cough that redox active center is basically that perylene center. And what is happening? This is basically the mechanism of the 2-electron reduction over there in that perylene moiety, and you can see that CO bond basically can be reduced to give some polar structure and bipolar structure. So basically that dot minus and that minus, that di-anion basically by means of this voltage, and we can see these things. So that stepwise reduction of the material can give something kind of multicolor electrochromism over there. So from yellow to purple to that brownish color basically, and it can give something kind of that NIR absorption over there over 1000 nanometer when it is fully reduced by 1.5 volts, that negative 1.5 volt. As this structure is basically the covalent polymeric structure that is having intrinsically that pores basically, and that ion diffusion is very swift, and we can get something kind of TB, means that bleaching time and coloration time very fast over there. A very stable system basically. We started the stability, and most importantly that solar light block. So that full solar irradiance is blocked by 68% over there when we use the fully reduced state. And coloration efficiency also we got 183 centimeter inverse per coulomb. So basically this is not so high, I can tell, but this is kind of moderate. But power and energy consumption for this kind of electrochromic film is very low. But the thing is that we cannot block the sunlight to the fullest. So 68% blocking. So for that, actually, we went to that metal supramolecular polymer structure. So for that, our strategy was that we can use some cobalt as that metal over there, so that reducible cobalt 2 center can produce the cobalt 1 over there. So we first we synthesized that tarpidine CHO containing tarpidine, so aldehyde containing tarpidine, and then by something kind of polycondensation, that condensation reaction, we have generated this ligand tarpidine, the thiazole and tarpidine. So this is a ditopic ligand. When we charge with copper, that cobalt acetate, we got the polymer. And that polymer, one important thing actually over here, that NMR, so stepwise NMR we have produced over there. So this is the NMR of this ligand, and you see that ppm value over here, it is around that 7 to 9. But whenever it is complexed with cobalt, due to this anisotropy, so basically that magnetic anisotropy, it is giving that ppm value very high over here, and the ppm value is basically around 100 over here in this cobalt complex. And we did that HRMS also, that gradual mass spectroscopy also we did, so that that kind of characterization part I am not going due to the time constraint. So I'll show that visible to NIR electrochromic behavior of this material in the solid state device basically. So initially it is pale yellow in color, but whenever it is reduced the cobalt center, it is giving something kind of brownish black kind of color. So this is associated with the reduction of the cobalt center to cobalt 1, and then that reversible oxidation is also there for this cobalt 1 to cobalt 2, and it is associated with the transmittance change between the states, and it is purely that highly durable, and that coloration time is basically 8 seconds, and that bleaching time is around 10.7. So coloration time means that time required for this yellow to black and black to yellow is the bleaching time. That important thing is solar irradiation blocking. So what we find that it can block around 70% of the solar radiation when you use the dark hue of this electrochromic device over there. And another thing that if it can cut down that solar irradiance by 70%, so it can that room temperature, what actually that initially I told, that room temperature will be cool enough. So to prove that concept, basically, we have designed one miniature room, basically, so miniature home, and that home is nothing but that thermocol home we just developed. And in that thermocol home, we have installed that electrochromic display, our fabricated electrochromic device as the window, and through the window we have given that we have irradiated that IR light continuously for that time interval, and in different time interval we measure the inside temperature. For measuring the inside temperature, we kept one object inside the box, basically the box type foam, and inside the box type foam we kept one glass vial along with the water. So through the IR camera, we measure the temperature of this glass vial. So after 15 minutes of the irradiation, when it is there in the transparent hue, means that yellow hue, we find the temperature raised to 44 degree from the room temperature, and room temperature was around 25 degree. And after 30 minutes, it was 51 when you use the yellow setting. But when you use the dark hue, the temperature after 15 minutes is basically 36, and after 30 minutes it is 41. So if you compare with that 51 to 41, so 10 degree, we can reduce 10 degree inside temperature basically by using this smart window. And not only that, we have checked with the transparent glass window basically, and glass window after 30 minutes, if you continuously irradiate the IR light, it goes to 85 degree. So it's a huge 85 degree. Sunlight is having only 50% IR, so that is why that room temperature is not increased much. But that room temperature probably it can goes to, in our summer it can goes to 50 degree even in certain cases in certain cities. So it can effectively reduce that. But the thing is that it cannot cut down the full solar irradiance. So in that way, we find that this color is basically that brownish black. So brownish black means that brown color is associated with that, and that brown color is coming probably from this thiazole part, and this conjugated organic ligand can give something kind of color over there. And that is why we started this thing, and that we can cut down that organic part basically over there in that complex. So we developed another complex where that organic ligand size is very small. Okay, along with that, we can introduce some porosity inside the polymer, not polymeric structure actually. That polymeric structure earlier was the one-dimensional polymer, which was not having any intrinsic pore over there. But if we can provide this kind of square complex, then we can generate some pores also, and that pore are required basically for swift ion diffusion over there. So we have prepared this, and we have characterized well by kind of that NMR, that other spectroscopic techniques, that mass spectroscopy, and also by something kind of that photophysical studies like UV visible and emission studies. Emission actually very unique for this kind of platinum complex. So what is happening, that platinum complex, to make this kind of, so that cobalt complex we have prepared first, and cobalt complex we use something kind of platinum complex over there to just joining this cobalt complex in a square that size, basically square shape. So this platinum complex is very unique if it can have something kind of aggregation inside. So it can give something kind of dinuclear platinum, that MLCT, that emission inside, and it can give something kind of red emission over there. And that is very unique for this platinum or even gold or even palladium kind of metals. It's a porous structure, and having something kind of pore around 50, that surface area around 50 meters per gram. 2.1 nanometer is the pore size, and that is actually matched with the molecular pore size of this material. And most importantly, we have studied the high resolution TEM study, and we can find that square complex, individual square complex also over there. And this electrochromic study, whenever we are doing that reduced state, basically is showing something kind of black color over there, pure black. And you can see that reduced state is basically absorb all that UV and also that IR. And what happened, that color fastness is around similar what actually was there earlier, so we cannot reduce the color that fastness over there. So switching time is kind of similar, but is also very stable and durable. But that key thing is basically over here, we can reduce the solar irradiance through this window by 99.97%. And similar kind of so this is basically why the need of this square architecture. And if you don't use the square architecture, that cobalt complex is basically not giving a good film. To get the film, that platinum part is much important. And also this is not that much of durable basically if you use only the cobalt complex with this targeted ligand. Okay, and the switching time is also very high. So targeting is playing the role to give this kind of square complex structure, which is giving that better ion movement over there. And that another thing, actually, the metal to metal, that electron transfer through this electron hopping in this kind of nanoseed structure, which I showed over there earlier. So that nanoseed structure basically can if you can see, so this is basically giving something kind of aggregation over there inside the material. And another thing, actually, by something kind of DFT study, we established that platinum is having something kind of d-pi-p-pi bond with this targeted in nitrogen, and as a whole, that whole complex will be electronically delocalized. So that is also important for any kind of that pseudo-capacitance material or Faradic material that electron transfer is required for better fast oxidation or reduction. And that box, that miniature box kind of study also we did with these things, and we can find that after 5 minutes of irradiation, so this column is basically that orange state or the neutral state, and this is the black state basically. So from 31, after 5 minutes, it was 31, that orange state, 36 and 37. But here, that dark state is not showing any temperature change inside the box. Okay, and that box is also that window is also having kind of that optical memory. After 15 minutes also, that blackish color is still there, so it can run without the power also. So the conclusion over here, actually, we can generate different. We can generate the complete truly black color over there, and that black color can prevent the solar irradiance, which actually is useful to keep the room temperature cool. So another part of my talk is basically the thing is we can generate the smart window, but that smart window is basically the mechanism if we see for this electrochemical device is kind of as similar as the battery or supercapacitor, especially the CO2 capacitor. So can it store the charge? And can we use the smart window basically for your domestic purpose, like charging the mobile or even that laptop when the power will go? So basically, that thing is that your window can provide you the charge when you will be in a no power condition, basically. So in this purpose, we started that electrochemical energy storage behavior of this kind of windows. And these are the brief energy storage things. So in energy storage devices are basically the supercapacitor or battery. So capacitor are having very high power density but low energy density, but batteries are having battery or fuel cell, they are having something kind of high energy density but low power. That low power density will be there. But hybrid supercapacitor or even that Faradic material, which is that Faradic or that pseudo capacitor material, they are the asymmetric supercapacitor basically. They can provide high power density as well as high energy density, and that is required for that EVs. Okay, so that kind of electronic vehicles. Electric vehicles. So electric vehicles, suppose that high power density, so where it is required. So suppose you are going to a steeper slope. So you need some energy in some quick time. So that power density is coming into account. And whenever you are going to a smooth surface, basically you need some high energy density to run the car. So this energy storage, basically, mechanistically, it depends on three different kind of concepts like EDLC, electric double layer capacitance. So this is the that arrangement of the charge, and that usually is there in the capacitors. And pseudo capacitors, they are basically that supercapacitor. They are denoted as a supercapacitor. They can have some active material which is Faradic in nature, means that oxidation reduction both will be there, and other side can have something kind of active material that can have again that oxidation reduction also. And another is the hybrid supercapacitor, where one side will be the active material having Faradic process, and other side can have something kind of EDLC, and that exactly is there in the battery or even that hybrid supercapacitors. So in this concept, we developed one metallopolymer over here. That metallopolymer is having the some kind of that iron as the electrochemical center, means that redox active center. But what we did, we have produced this ligand, keeping in mind that we have cut down the that conjugation over there. So if you cut down the conjugation over there, I told earlier that it can block the electron transfer between the iron centers. So what will happen, that it can produce something kind of self-bleaching can be restricted over there, and that can probably give something kind of better data in that kind of discharge time. So basically the discharge time in that energy storage will be a little bit higher over there. So we synthesize that. We have characterized through UV visible spectra, FTIR, and also SEM index studies. And in SEM, you can see this one-dimensional polymeric fibers we got out of this polymer. So this is a device structure to produce that solid state device over there that can show the color change from purple to colorless over here in these iron containing polymers, and it is associated with the iron +2 to +3. During the charging, that iron +2 is going to +3, and during the discharging, it is going back to its original pristine iron +2 form. And it is associated with the transmittance change, means optical, that optical contrast is around 47% over there. It's very stable, and that color fastness is very high, 1.5 second to 2.4 second, and it is having that optical memory also. But we told that we cut down that conjugation over there, so that conjugation actually is preventing that electronic communication, and it is giving something kind of optical memory over there. So can you please mute? Okay, so that electrochemic energy storage property also is studied. So that energy storage studies, we exclusively studies that supercapacity property over there in defined current that density basically, and that supercapacity property we evaluated as that volumetric capacitance is around 70 at 1 ampere per centimeter cube, that current density basically. So this color change is also associated with this energy storage, and we have established that. And the thing is that that most importantly, this energy storage is associated with the color change. Suppose in any kind of wearable device, so by looking, or even that window, smart window, by looking the color of the window, you can tell that what actually the energy state over there. So how many percentage of the charge is being stored over there or in this material. So that is one. Another example I quickly, so probably I'm just running out the time. Swagata, how many time I'm remaining, or it is done?
You take 2 to 3 minutes. Okay,
I'll just 5 minutes more. I'll just take. Sorry. So this here actually we have introduced good communication over there. So last example I showed that bad communication, but here the good communication, and let's see what happened. And what we find that electronic communication between two iron thing, actually we put better by means of these conjugated ligands over there, that benzo-thiazole containing ligand. And what we got that I'll quickly go to that energy storage studies basically. Here we got around 70. So that value is kind of similar. Probably that actually that electronic communication as well as that acceptor property of this benzo-thiazole ligand is also playing the role over there. But the thing is, here the energy density is enhanced over there. So basically, electronic communication can also enhance. Electronic communication between this iron center can also enhance the property over there. What we thought earlier that that can produce the optical memory. Yes, that produce the optical memory in that last example here. But the thing is that optical memory. Over the optical memory, that electronic communication is giving the better energy density over there in that particular material. And we also actually we have prepared that poly-Fe, one polymer having no this thiazole part. So the thiazole part we that not thiazole benzothiazole part actually we omitted by means only one phenyl group. So that polymer also we prepared, and if we can compare that actually that. Property basically that volumetric capacitance property is better over there in this benzothiazole containing polymer over there. So we established that good electronic communication between the redox centers can provide better that better energy storage property, and when we use the device over there in that charged condition, it can glow the what is called that LED panel. Next example, I'll just skip over there. So here, or even I just quickly tell that this is basically one polymer we have synthesized over here to enhance to provide some structural engineering to enhance the surface area and introduce the porosity by means of this interfacial polymerization. So these are the two-dimensional nanosheet structure we have generated out of the metallo-supramolecular polymer, and that gives the stable that electrochromism over there, and that optical memory. So if you see the structure basically here, that non-conjugation is associated with that. So that non-conjugation is providing a lot of optical memory over there, and that material is that electrochromic device can get the color, intrinsic color back in open circuit condition, probably in 48 hours. Okay, that full color back. So enough optical memory is there, and we introduce that enough optical memory, and we find in that energy storage basically, and we find that volumetric capacitance is quite high over there, and it's around 250 in that device. So this is very high. So from earlier example, if you remember, it was around 70, but here we got around 250. It can go the LED bulbs, and we have correlated that electrochromism along with the energy storage basically, as like we did earlier also. So that surface area increment, or even that surface along with the surface area, that porosity can generate that can enhance the energy storage property over there in that smart window. Here, this example I'll skip, and I'll directly go to here. Actually, quickly I can tell that this is the polymer with ruthenium ion over there. So ruthenium is also another electrochromic center basically. So that can give something kind of color change from ruthenium +2 to +3 associated with the color change from red to green. And we introduced POS. POS is a polyhedral oligomeric cis-cohexane, and this can produce a better surface area over there in that composite, and that better surface area can give that better result in that electrochromic color fastness as well as the capacitance values also over there. And we have produced some large scale device also, so scaling up also we did, and that in that kind of fully charged state basically it can glow the LED panel. And as a conclusion, I can tell that we have developed some power efficient smart window in our lab, and also that smart window can effectively block the sunlight as well as it can be used as the energy source or the power source basically for domestic use. And I would like to acknowledge the funding agencies. So DST Inspire, of course, and then that ACRB, ICMR, and DST for several projects actually that funded my research along with my students basically. At present in my lab, 9 students are there working effectively for this kind of research. And today what the research I have presented over here, so exclusively that was done by Dr. Sayan. Sayan just got the PhD degree last month only, and Dr. Sushmita, she was my first student, and Pallavi. And thank you so much for your presence.